Hello everyone, July 11th. Alright, let's get right to it. I think I've done this before. So I'll do this and try to see if we can fix this thing. Alright, find eventual safe state. Actually, no, it looks new. Maybe I haven't done this before. There is a directed graph of n nodes with each node labeled from 0 to n minus 1. The graph is represented by a 0 indexed to the integer array. A graph I is an integer array of nodes adjacent to node I, meaning there is an edge from node I to each node. Okay. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node, which means there's no cycles, right? Is that what it means? And it's a directed graph. Return an array containing all the safe nodes. The answer should be sorted in ascending order. Sorting is fine. Okay, so 0 go to 1 and 2. 2 go to... No, 1 go to 2 and 3. 3 go to... Come on, 2 go to 5. 3 go to 0. 4 go to 5. 5 doesn't go anywhere. 6 doesn't go anywhere. So while we're looking at this, 5 and 6 are terminal node. And a node is safe if every possible path starting from that node leads to a terminal node. So in this case, 2 can go to 5. So 2 is good. 4 go to 5. 4 is good. 5 and 6, they themselves be good. But 1 is not good because 1 go to 2, but there's another path from 2 can go to 0, and 0 go to 1. So we have a circle. So 1 is not. And 0 is not, because 0 go to 1. 0 can go to 2. Well, 0 to 2, it works, but 0 go to 1, because 1 is bad. So 0 must be bad, right? Because 1 can go into a cycle, which means from 0 there is at least one way that can go into a cycle. Okay. 3 is bad because 3 go to 0. And 0 is bad, so that's why 3 is bad. What do you think? Graph I is sorted in a strictly increasing order. The graph may contain self-loops. Alright, so we go through everything so we can find out which ones are the terminal node, right? We can find out which one is the terminal node. The terminal node, which means it's just empty, right? So these will go into the result. And then the question is, maybe we can go backwards, right? Because people who arrive at this, so we can actually go through this and then point the edges backwards. So like I'm at 5. So if I point backwards, is 4 and 2, right? So we know 4 and 2 has the potential to reach 5. So now we look at 4. Yeah, hold on. Because we say every, right? Every. If every possible path, right, has to end, which means if we go backwards, every path has to end up at one of those. So every single node in the path are safe. Every single one, because if there's one thing that's not safe, then it's no good. So every single node has to be safe. So we go backwards. We know who is a terminal node. So we go 1 backwards, right? 1 backwards. And it's like 1 level, 1 backwards. And if any one of them do not have other paths, then this is a safe node. What if they do have other paths, like 2, right? 2 have other paths. That's actually no, 2 doesn't have any paths. 2 is the end. 2 is the end. Oh, I think this is topological sort. You look for the one that have no in edges, right? Then you go for stuff that, right, and then you remove these, and you go for the next one that does not have out edges. My bad. Does not have out edges, right? And then you keep going, and until you cannot find something without out edges, and that's it. Topological sort. Topological sort. Because what you want is every step, every single node, you go back, you go from the terminal node backwards. Every single node has to be basically terminal node once you remove the terminal node. So topological sort will do. Sorry, it's too many windows open. Okay. Topological sort. What do we need? We need a heap. Then we need the number of out edges, right? The number of out edges. We don't need a graph. We just need number of out edges. And we need to delete. We need to turn everything into a, yeah, because we go 5 and 6 will push into, well, 5 and 6 will be already in it, right? And everybody will be in the heap. So 5 and 6 pop out first, and then we handle it. And we need to know who goes to 5, right? We need to know who goes to 5. Right? Who goes to 5? So I know who goes to 5 because as I go through, I can say 5's parent. Okay, 5's parent is whom. Then we go to those. We reduce their value. Right? We reduce their value. And now if we reduce, we push them back in. Right? We push them back in. And I push them back in. Do I need to have a central state to keep track of the number of out edges on every single one? And honestly, I mean, I can, but a better way will be, if you turn this into a set, so every time we can remove, right? I don't like it. So you have 5, right? You find the parents of 2, 3, so you remove. Okay. Now you add 2. Who's the parent of 2? So go to those. Because every single one will only be visited once, right? So who's the parent of 2? And you check who the parent of 2 is. And yeah, I think we don't have to do that, but we do need to have a different, not a graph, so we say parents, right? Parents will be same thing, n equal to len graph, right? So parents will equal to this. No, it's not equal to this. It's equal to this for this in range n. Might as well. This might be faster. Okay. Then for I, children, enumerate graph, right? Then we say for Oof. I have to go through every single one. Open it up. Ooh. Number of edges. Oh, it says will be in the range. That's fine. So for child and children, we say parents, child, dot append, I. Right? Dot append I. So we know when we go to this child, who are the parents. So we go to the parents, we decrement their thing. So okay, so this is the parents, and we need to say num out edges. Oh, I probably need to do this one here. 0 times n, and then q equal to this. All right. So we do this, then num out edges I equal to len children. This is the number of out edges, okay? And then heap dot heap push q. Who gets pushed in? Actually, no. We'll push in only the one that's 0. I'm gonna say if num out edges I equal to 0, then we push them in. We're only pushing the things that's 0, right? Okay, so what do we push in? We need to push in 0, number of edges, and I. So once we've done this, we have everything ready. Now we can say while q, all right, and we are going to pop out. Actually, we don't need to pop out. We just need to check. We need a result as well. So we just need to check. We say if q 0 and 0 is not equal to 0, then we'll break. We cannot do anymore. Otherwise, we can say this node equals heap q dot heap pop q. Pop one out. We got a node, rest dot append node. Okay. Then what? Then you need to check its parent. Right? We can say for p for pair in parents node, right? It's node's parent. For each one of them, num out edges parent minus equal 1. If num out edges parent is equal to 0, then we say heap q. Then why do you use heap? Right? Why do you use heap? Right? Why do you use heap? If you're only gonna push 0 in, then I don't think you need to use heap. I think q will be enough. Dot append 0 and I. No, just append I. That's it. You don't even need to append 0, right? When you say if, that's fine. We just keep going, right? And I cannot pop. All right, let's see. From collections, import deck. Haven't used deck for a while. Node equals q dot pop left. This add to it. This, if this is, then we say q dot append parent. So we go through all that. Then keep going. Now return rest, sorted rest. All right, let's give this a shot. 2, 4, 5, 6. That's 4. Eventual safe nodes. Looks right. How about we just test 1? Good test cases. Oh, invalid test case, my bad. Number of edges to have between, oh, we have to have at least 1 edge. Does this one work? Nope. We have to have at least 1 edge. Alright, that's fine. So we can go to 1. Okay, so and then we can go to 1. That have at least 1 edge for all of them. Looks to be right. Okay, let's give it a shot. It's slow, but it works. So this is like a topological sort. I use topological sort and going from the terminal nodes backwards, right? It is guaranteed that each node in the safe path must also be terminal nodes when their adjacent terminal nodes are removed. Thus, we keep track of the number of out edges for each node, right? For each node, and BFS, basically BFS from terminal nodes back. We add the result, we add to the answer all the nodes during BFS that end up with 0 out edges. We do have to create this parent thing. This is not really nice, but I don't see how we can avoid it. And I also use this. I don't see how we can avoid it. Alright, time to see the solution. Topological sort using Kahn's algorithm. I haven't heard of Kahn's algorithm before. Alright, let's just take a look. In degrees. In degrees. Why do you do in degrees? Yeah, this is OM. Yeah, I forgot to do this. Because this is OM, we have to go through all the edges. This is all the nodes. So OM plus N. But why are you doing in degrees? For node in graph I, for I in everything, for node in graph I, adjacent node, that's the parent. So in degrees plus equal 1. I, graph I, Now I think in degree is going out. I think this in degree is going out. Yeah, in degree it's going out because they say in degree. In degree. Yeah, if you think about it reverse, right? If you reverse it, then that makes sense. Yeah, this is doing reverse degrees. So I think this is the same, right? So we do this, get this, safe, and then we do this. Yeah, I think that's exactly the same as how we do it. It's the same. DFS. DFS to find the path. We can use our cursor to explore nodes as far as possible. So as long as some gets if anyone get into a cycle, then this is an unsafe node. Anyone that can lead, all the paths can lead to a safe node. Can you just DFS it? You just DFS it, right? You DFS it. You're starting from whichever node, and you DFS. And you know what? I want to try. I'm not reading it, the solution. I just have some idea. What if I just DFS it? You know, we can say, yeah, is safe. That's a good one. Right, is safe and be false times n. Okay, and def DFS, we have a node, and we're gonna return a Boolean value. Right, and we have, say, path. That's gonna be a set. Right, let's do a set. So what my ideal is, I'm a node, so I look for my next one, right? So we say if node in path return false. That's bad. If node in path, then is safe node. Yeah, we just don't make any changes, right? Otherwise, if node is not in path, path.add node, and then for child in graph node. DFS child path. If I've had to go through everything, right? If everything is true, right? If everything is true, which means if all of this if this is in path, or now if this is in path, return false. Hold a second. We also need a case of not visited, right? Okay, let's do this. -1 means it's not visited. Okay, is safe. So if node in path or is safe node equal to 0, then is safe node equal to 0, and now return. Okay. Otherwise, if is safe node is equal to 1, return true. Right? Otherwise, we haven't visited, we add this, and we say if all of this is true, if all is true, then is safe node equal to 1, and then return true. Otherwise, is safe node equal to 0, return false. If node in path or this equal to 0, if not, if this or graph node, right? Graph node, not graph node. Then we'll set this to 1 and now return true. Otherwise, we do all this. Actually, that's a good question. I don't know. I'm gonna PT Python this thing. What's B? B is true. So this will be true. Oh, actually, wait, I cannot do it this way. Cannot do it this way. Path add. Oh, I can. I can. Path add, I'm gonna do all this. And remove node, because it's, I have to do this path remove node. So when you say for I in range n, if is safe I smaller than 0, DFS I, and then return for I in range n, if is safe I equal to 1. Alright, does this one work? Path, didn't do path. Yeah, it's not right. Why? Why this one doesn't work? So we start from 0. 0 to 1. I'm missing the ones. I'm missing 5 and 6. Actually, we should do it here. So I have 5. 5 not in path. Graph 5. Shouldn't this already? Yeah, we got 5. I just set it to 1. That's bonkers. I already set it to 1. Oh, my bad. Got it wrong. Equal to 1. Come on. Yep, that should work. So this is a DFS. Inspired by the official solution. The ideal is to traverse, right, the graph. Thanks. A node is safe if all the paths lead to safe nodes. As long as one path has cycle, the node is unsafe. And each node only needs to be visited once. I should probably say M is the number of edges and N is the number of nodes. Alright, let's try this. Alright, looks good. Oh! What? We scored exactly the same. Suspicious. Suspicious. Alright, so we're done with this one. I'm gonna move on. Okay, so this is the one we failed yesterday, right? So what it's saying is if we have DACD and I return DCAB because I say everything has to be AB, right? It has to be AB. But here, this is A, right? So we can go to B, right? And B is equal to this because by default I set to AB, right? So we set this one first. Right? And then the current will go up. So I'm going to check, right? So the current, if the current is equal to, if the current is B, basically that's the only case. If the current is B, then we'll have a case of, right? So we have D, A, C, D, right? So this can now go. So actually we go to D, A, B. Now this go up. So this one turned into B. But now this and this is the same. And the current logic is if they are the same, R line equal to 1, this has to not equal to, right first has to not equal to, I should say this is right first. First letter to the right of SI. And it's actually no, actually it's this one. Right, R line equal to 2 because these two are the same. And RS is not equal to, that's good. And if RS equal to 0, then current cannot equal to 1, but now current is 1, right? So in this case, I say I will increase this to C, right? Now I get to DCAB. But it's wrong, because in this case, I can maintain this, but change this, because I want to maintain this, right? So this cannot be B. So I want this to be as small as possible. And here I cannot be B. So this one can only be C. And this one should be A. No, that's not right. DBAB. I say this. Oh yeah, I just turn this into C. Right? Turn this into C. So what I'm saying is, if this and this are the same, we shall try to increment this one. Right? We try to increment this one. And it's after this one gets incremented, right? So this one is incremented, and this one's already the smallest we can get. And if these are the same, if these two are the same, oh, so this gets incremented, right? What if this is B? We have a BB situation. We should try to increment this. Increment this into C. Because we have the current situation is either ABC or BAC, right? ABC is always safe, but if these two are the same, then we shall do ACB. Right? Okay, let's see. This is what we consider, right? So this cannot be A, so this is B. If this is B, BACB is good. BABC is not good. So if this is B, this has to be ACB. Okay? If this is C, then it has to be ABC. C or larger is going to be ABC. If this is going to be A, then this has to be BAC. If this is going to be B, then this is going to be ABC. B plus, right? It's going to be ABC. So these are the four situations. These are the four situations. So the four situations is ACB, ABC, BAC. So the only deviation is if this is A and if this is B. That's the only deviation. And what if we have an A and a B? Then what do we do? So because it's A, we have to do BAC, right? And since it's a B, this has to be ACB, but it cannot be B. So I shall check both. Okay? At a current position, I see what the current is. If the current is C or plus, default ABC. Then I check the one in front. If the one in front is A, this has to be BAC. Right? If this position is B, default is ACB. Right? Now we check in front. If front is A, holy crap. If front is A, what do we do? If we have AB, if we have AB, then we can now do A, nor can we do B. So it has to be C, right? And can we do A? Yes. So CAB. So it's CAB. If it's an AB, then it's CAB. All right, so you want to summarize it, right? So here's a summary. This position. And what's this? If it's a B, this has to be ACB. If we have an AB, then this has to be CAB. If this is a A, but this is not a B, then we do, this is like C plus. Then we do BAC. If this is a B plus, and this is a C plus, then we do ABC. I think these are the cases. So maybe we can redo it. This is right. Okay, the first one is right. Maybe here we can do R length. That's fine. R length. Okay, so with all these cases, well, we can say if R length is equal to 0, then we shall just increment, right? If R equal to 0, then we can actually do the current. This is the current. And current equal to this. Then we say if and current is smaller than K, then we can basically return. Because it's the last one, and if an increment it works, then it will work. Ooh, what if it's equal to? So we still have to, bring everybody together. Okay, okie dokie. So I think it should be while K here, while current smaller than K. Okay. Then we need to do checks. Okay, we need to do checks. What's the check? To see if everything passes, then we can go up. If not, so we can do checks. Then it should be any of these passes, right? It shouldn't be all. So 1 check equal to 0. Right? If AC equal to 0, then, and also current cannot equal to the hold on, basic check, current not equal to, so if I minus 1 is if I don't have anything on the left, then this check basically pass. Right? So we say this one's smaller than 0, then we don't have check on the left. So that's 1. If this is true, then will pass. Okay, this is will pass. And you know what? Lots of checks. There are a lot of checks. Yeah, I'll say if I minus 1 is smaller than 0, there's nothing to check on the left-hand side, right? There's nothing to check on the left-hand side. Then we can just do whatever the current it is, and it'll work. So now we're going to say what the current is, right? What the current is. And a current, if it's a B, right? If current is a B, then right pattern shall be ACB. Else, right pattern shall be ABC. Okay. Else. Oh, we have to check both. Right, L if I minus 1 is equal to 0. Right, equal to 0, and current is not equal to this, and this is not equal to. Oh, it's not B, it's 1. That'll be the same, right? Our pattern. Oh, not necessarily, right? So they're not the same. So it could be this case. Well, depends, right? So we say if current is equal to 1, which is the B situation. Now we say if this is equal to 0, it's an A, then right pattern is going to be CAB. Else this is not an A, and these are not, so it's going to be C or more. So that's going to be ACB. That's if this is 1, right? Else, so it's C or plus. Again, we're going to check these two. If this is A, then this is going to be BAC. Otherwise, that's going to be ABC. Okay. If I minus 1 larger than 0. And this satisfies, and this satisfied. Minus 2. All right, hold on. I need to feed a cat. Yes. 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 some meows in the video. Yeah, put him on the ground. Good catch. Alright, let's keep going. Where are we? So this is not equal to, and this is not equal to. Yeah, basically just say the current cannot equal to the one in front, cannot equal to the two in front. So if that is the case, I think it's the same, isn't it? Right? That is exactly the same. If current is B, we do this. If current is not B, we do the other thing. So maybe we can do if this or this, because they are exactly the same. Okay. What else? Well, I feel like that's it. Right? That's it. We check if we have nothing on the left. So, yeah, if there's nothing on the left, whatever you change, that's fine. If you have one thing in the left, then you do all these checks. If I have two things in the left, you do one more check. And if none of them works, then you'll do I think once you get the so we'll break here, and this is the same. You go to 1. That basically means we're good, right? That just means we're good. I'll break, right? Otherwise, current plus equal 1. So else, continue. That just failed. We didn't find anything. Otherwise, we have found something. So we'll do this. Okay, does this work? It works for all these test cases, so we can give this a shot. if this is wrong. Oh! Ah! We got this! I was just going to say if this is wrong, I'm going to give up because it's already about 1 hour. Oh. Oh, it works. It works. And very fast. Look, 90%. 90 percentile. That was very unexpected. I did not expect this to pass, actually. Well, good surprise. All right, let's summarize the method. What's the thought process behind this? Well, to begin with, we go from right to left, right? And we can determine the we go right to left. Suppose we are currently at position SI, okay? Then S the pattern of SI to the end, I plus 1 to the end, is deterministic. Depending on the letter SI, depending on what SI is I minus 1 and is I minus 1 if it exists R. Now the pattern of SI plus 1 must be a repeat of triplets. The smallest of all is ABC, 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 is a repeat. Is a yes, for sure. Oh, sorry, I forgot to mention it, please. That's okay. Repeat of ABC, because any other combinations will surely be bigger. Any other combinations do not satisfy the requirement of no palindrome. However, we cannot always use ABC. Now, here are the cases that determine which triplets we shall use. If SI is equal to B, note that SI can never be A. Then the triplet, now if I triplet B, then if SI minus 1 is equal to A, triplet shall equal to that was this case. This case is CAB. Else triplet equal to ACB, right? Else, if SI minus 1 equal to A, triplet equal to BAC. Else, triplet equal to ABC. Right. So the solution is basically following this rule. It's a little bit complicated following this rule, right? Okay, now use it however. But before we can follow this rule, we have to make sure SI. No, I shouldn't say SI. Now, can now use errors in case to determine if, say, current, right? Say we have determined that current is a valid letter for SI. Then this is not SI. Current, right? Current, have to make sure current is valid, right? To make current valid, we don't have to check the pattern on the right because the triplet choices have already done the check. What we need to do is to check the pattern on the left. Now, if we have more than 2 letters on the left, we have to make sure that current not equal to SI minus 1 and current not equal to SI minus 2, right? If we only have 1 letter on the left, then current not equal to SI minus 1. If there is nothing on the left, we don't have to check, right? Now the final solution is basically to combine all these if-else together and implement a mechanism to increment current if it fails, right? And that's it. That's basically how it is. So it would be ON times K, right? ON times K. And we have very good performance. All right, cool. I wonder if I don't need this. Yeah, I don't even need this. I'm gonna submit this one again with all the explanations. Yeah, I don't need the single one because this will basically, this is 0. I will be 0, right? rlan, oh, we don't even need rlan. Never use rlan. That will be 0. And oh, I did use rlan. Oh shoot, I did use rlan. All right, how about we do this? Len s. We swap this to n minus I minus 1, right? That's n minus I minus 1. So this is n minus I minus 1. There we go. So I is 0. This is whatever it is. If it's smaller than, then we check, and this is this case, right? And we have this. And because this is 0, so QR will all be 0. So we'll be, yeah, that's why it makes sense, right? That's why it makes sense. Okay, this is my final one. Submit this. Then we'll call it today. Oh! Ooh, we got even faster. My God. So tomorrow, what we're gonna do, we're gonna check the solutions. All right, we'll check the solutions. Weird problem. All right, that will be it. Maybe we can post this. Yeah, maybe we can post this. Anyway, I will see you guys tomorrow. Adios.